In this unit, we'll introduce the concept of a two-force member. First, some notes regarding two-force members and how we identify them in our analysis problems. One thing to note is that identifying two-force members is not strictly necessary. It really just usually simplifies the analysis. And in doing that, reduces the possibility of making errors, and that's always one of our objectives. So to identify two-force members in a structure, we look for individual members that satisfy the following. 1. Members whose weight is negligible compared to the applied loads. 2. We look for members that are connected by exactly two pin connections. Recall that the interaction at a pin connection is a force of an unknown magnitude and an unknown direction. And then lastly, 3, members that have no applied loading between connections. So if we can find those things, those 3 things, we usually have a two-force member, and identifying them usually simplifies our analysis. So a two-force member is exactly what the name implies. It's a member, and we'll show just kind of a blob here as our member with two forces applied to it. A force at point A, we'll call that FA, and a force at a point B, we'll call that FB. And so we have an unknown magnitude and direction of FA and of FB. So note for this two-force member, a member that has exactly two forces applied to it, we have 4 unknowns. So at A we have an unknown force and an unknown direction, and we'll look at the direction to be the angle that the force makes with the vertical, and the same thing at B. And we'll call the angles phi sub A and phi sub B, and the unknown magnitudes FA and FB. Recall that we have 3 independent equations of equilibrium available to us to solve for these 4 unknowns. And we won't be able to find them uniquely since we don't have enough equations. We have more unknowns than we have equations, but we can find relationships between these 4 unknowns. So let's look at taking moment equilibrium about point A. And so our force FA is concurrent about point A, so we won't learn too much about that force. But FB, in order to have equilibrium, both FA and FB have to be concurrent about point A, and so we still don't know what the magnitude of FB is, but we know that its line of action has to be along the line between A and B. So we find one thing out. We know the line of action of the force applied at B has to pass through point A. Now let's look at rotational equilibrium or moment equilibrium about point B. And so our force at B is concurrent about point B, but for rotational equilibrium about point B, we find that the force applied at A has to be along the line between points A and B to be concurrent with point B. So we still don't know the magnitude of the force applied at A, and we still don't know the magnitude of the force applied at point B, but we know that both their lines of action have to be on the line between the point where the forces are applied, in this case A and B. So at this point, we've used up 2 of our equations of equilibrium. We have 1 more independent equation of equilibrium remaining, and we still have 2 unknowns, the magnitudes of those 2 forces at A and B. It's convenient for us, in this particular case and in certain problems, to align a coordinate system in a preferred direction. In this case, let's line our coordinate system up so that the x-axis is along the line between points A and B, and then the y-axis is perpendicular to that. And so we'll look at force equilibrium in the x direction, or along the line between points A and B. So we'll write our equation of equilibrium in the x direction. So we have Fa acting in the positive x direction and Fb acting in the positive x direction. And for equilibrium in that direction, those two have to sum to be equal to 0. And so what we find is that Fa has to be equal to minus Fb. And so what we see is that the magnitudes of these two forces would have to be the same, and they would have to have opposite sense. So the forces at A and B have to be equal in magnitude and opposite in sense. So from our three equilibrium equations, we find that the forces at A and B have to be equal in magnitude, opposite in sense, and have to have the same line of action, and that lies between the 2 points where the forces are applied, in this case A and B. And then we have one unknown. We don't know what the magnitude of that force is, but equal in magnitude, opposite in sense. And so there's two possibilities. Those forces can be directed towards one another at A and B, as shown in the upper left-hand free body, or they could be directed away from one another. And so the only unknown remaining is the magnitude of the force. When we do our equilibrium calculations, we'll see with a two-force member that we'll guess whether the forces are either directed away from one another or directed towards one another, and the sign of our result will tell us if we've guessed right or the opposite sense, and we'll find the magnitude of that force. Note that the shape of the member between the 2 points of force application doesn't matter. So the whole idea with a two-force member is exactly what the name implies. There are exactly two forces applied to the member, and those two forces have to be equal in magnitude, directed towards one another, or directed away from one another. An example on campus of a structure that contains two force members is at the new rec center. We have some seismic frames that are designed to resist lateral load from earthquake, and these members or braces can resist a high amount of axial load or load along the length of the brace. We usually idealize the connections at the ends as pin connections, and in steel, the amount of axial force that can be carried is much, much greater than the weight, and so we usually take the weight to be negligible often in steel calculations, and we would in this case of designing these braces. And so these braces can be idealized as two force members. We have a force at each end of the brace, and so the brace can be in what we call compression, where the force in the brace is directed towards each other, or the brace can be in what we call tension, where the forces are directed away from one another, tending to extend the brace. So we can have tension or compression.